So the part of the dimensional analysis, in physics the word dimension denotes the physical nature of a quantity, right? So when we talk about the dimension, of course we're talking about a quantity. The distance between 2 points, for example, can be measured in feet, meters, or furlongs, which are different ways of expressing the dimension of length, right? The symbols used in this section to specify the dimension of length, mass, and time are L, M, and T respectively. Brackets will often used to denote the dimension of a physical quantity. And this notation, for example, the dimension of velocity v, so we put the velocity into the bracket, but the velocity is what? It's the length divided by the time. So that's the dimensional analysis for the v. And the dimension of the area, so the area is the length times the length, so it's a length square. The dimension of area, volume, velocity, and acceleration are listed in table 1.5 along with their units in the three common system. The dimension of other quantities such as the force and energy will be described later as they are introduced. And again, in physics, it's often necessary either to derive a mathematical expression or equation or to check its correctness. So a useful procedure for doing this is called the dimensional analysis, which makes use of the fact that dimensions can be treated as algebraic quantities, such as quantities can be added or subtracted only if they have same dimension. It follows that the terms on the opposite sides of an equation must have the same dimension. If they don't, the equation is wrong. If they do, the equation is probably correct, except for a possible constant factor. To illustrate this procedure, suppose we wish to derive a formula for the distance x traveled by a car in a time t if the car starts from the rest and moves with the constant acceleration a. The quantity x has a dimension, let x equal L, right? So x, it has the length, at time t, of course, has a dimension of the t. The acceleration is the change in velocity v with the time, because the v dimension of the length per unit of v we know is a length times divided by a time. Acceleration must be a L divided by time square. So we recognize that this information is kind of the equation that actually we derive for the acceleration. So if the acceleration is a v divided by dt, it is equal to L divided by a t divided by a t. So L t squared, which is equal to x divided by the t squared as well. Looking at this left and right hand sides of this equation, we might now guess that what is a and how we can calculate the a value. This expression is not quite correct, however, because there is a constant of proportionality, a simple numerical factor that cannot be determined solely through the dimensional analysis, as will be given in chapter 2. It turns out that the correct expression is x equal 1/2 at squared, right? So when we work algebraically with physical quantities, dimensional analysis allows us to check for errors in calculation, which often show up discrepancies in units. If, for example, the left-hand side of equation is in meters and the right-hand side is in a meter per second, we know immediately that we made some errors. So dimensional analysis is a good way for just deriving the equations. So for example, dimensional analysis of some of units of area, volume, velocity, and acceleration. So the meter square is for area, meter cube is for volume, velocity is the meter divided by s. acceleration is meter divided by s square, or centimeter square, centimeter cube, centimeter divided by s, centimeter s square, right? So the feet square, feet cube, feet divided by s, feet divided by s square, right? So analysis of equation. Check an equation using dimensional analysis. Show the expression for the v naught plus dt is dimensionally correct, where v and v naught is represent velocity, a represents acceleration, and t is the time interval. So for the v, what is that? We know is L divided by time, and the v naught is L divided by time. L divided by time squared is the velocity times the t. If we cancel out, so we get LT plus L divided by T equal LT. Right, so it's LT, we get the LT. So all terms agree. So equation is dimensionally correct, because all correct, because all terms they do agree. So we have like the true false equation is dimensionally correct is always physically up to a constant of the proportionality. So to determine whether the x v t squared is dimensionally correct, if not, provide the correct expression up to overcome. So x equal vt squared. So x is a length, v is a l divided times in the square. So it's so incorrect, right? So we don't have the x equal vt or even times t. We have t squared. We have x vt, right? So that's the correct way to do. Okay, so again, we're going to find the equation, use calculators to see how we can overcome. Okay. So another one that we can do is, let's see. Okay, derive the equation by using dimensional analysis. Find a relation between a constant acceleration, a speed v, and distance r from the origin for the particular traveling circle. So the strategy is what? Start with the terms having the most dimensionally, a, find its dimension, and then rewrite those dimension in terms of the dimension of the VR, and dimension of the time will be eliminated with v, because that's the only quantity in which a dimension appears. So if you want to write the a is a L divided by the time square, v is a L divided by t, now it says substitute the expression for t into a. So if you want to find the t, it is 1 over v. So if I put for t is a L divided 1 over v square. So it's going to be v squared divided by L. Now we can say that L equal to R, so it's going to be v squared divided by R, right? So it's my a that I drive it. So very simple and easy. Just you need to know the dimensional analysis and how you can substitute one value for the other one. So this is the correct equation for the centripetal acceleration. So if you have a centripetal acceleration towards the center of the motion to be discussed in chapter 7, in this case, it's not necessary to introduce a numerical factor such as a factor that displays explicitly as a constant k in front of the right hand, but we have the a equal kv squared divided by the r. So we can derive even the equations that we do not Not yet, and we did not learn about that. So that's a good thing. So true or false? Replacing the V by RT in the final answer also gives a dimensionally correct answer. So if we have the V, if I replace it by RT divided by R, if I square it, by R squared T squared divided by R, then it's going to be R squared T squared R, yeah. It gives me RT, and I don't think that is correct, but let's see. In physics, the energy E carries the dimension of the mass times the length squared divided by time squared. Use dimensional analysis to derive a relationship for the energy in terms of the mass and the speed up to constant proportionality to the speed equal to the c, the speed of the light, and the constant of proportionality equal to 1 to get the most famous equation in physics, right? So the answer that it came, we say E equal the m k v square, or we can get E mc square. The k is 1 and v equals c, right? So again, the hot topic in the physics is uncertainty in measurement and significant figures. Physics is a science in which mathematical laws are tested by experiment. Right? Experiment is very important in physics. No physical quantity can be determined with complete accuracy because our senses are physically limited, even when extended microscope, cyclotrons, and other gadgets. Knowing the experimental uncertainties in any measurement is very important. Without this information, little can be said about the final measurement. Using a crude scale, for example, we might find that the gold nugget has a mass of 3 kilograms. A prospective client interested in purchasing the nugget would naturally want to know about the accuracy of the measurement. To ensure paying a fair price, he wouldn't be happy to find that the measurement was good only to within a kilogram, because he might pay for 2 kilograms and only get 2, right? Of course, he might get 4 kilograms for the price of 3, but most people would be hesitate to gamble that an error would turn out in their favor. Accuracy of measurement depends on the sensitivity of apparatus, the skill of the person carrying out the measurement, and the number of the times the measurement is repeated. There are many ways handling uncertainties, and here we'll develop a basic and reliable method of keeping track of them in measurement itself and in subsequent calculation. Suppose that in a laboratory experiment we measure the area of a rectangle plate with a meter stick. Let's assume that the accuracy to which we can measure a particular dimension of the plate is a 0.01, so plus or minus. If the length of the plate is measured to be the 16.3 centimeter, we can claim only that it lies somewhere between 16.2 centimeter and 16.4 centimeter. In this case, we say that the measure value has 3 significant figures. Likewise, if the plate's width is measured to be 4.5 centimeter, the actual value lies between 4.4 centimeter and 4.6 centimeter. This measured value has only 2 significant figures, right? So it has a 2 significant. So if we say 4.6 or 4.5, it has 2 significant figure. Right, so we could write the measurement of the so we can write 16.3 plus or minus 0.1, right? In general, significant figure is reliably known digit other than a 0 used to locate a decimal point. Suppose we would like to find the area of the plate by multiplying the 2 measured values together. The final value can range between 16.3 minus 0.01 centimeter times 4.5 minus 0.01 centimeter or 71.28 centimeter, right? So claiming to know anything about the hundredths place or even the tenths place doesn't make any sense, because clearly we can't even be certain of the units place. whether it is 1 in 71 or the 5 in 75 or somewhere in between. The tens and the 100 plates are clearly not significant. We have some information about the units place, so the number is significant. Multiply the numbers at the middle of the uncertainty ranges gives like this, which is also a middle area for uncertainty range. Because of the hundreds and the tens are not significant, we drop them and make the answer to be 73 centimeters square with an accuracy of the plus or minus 2 centimeters square. Note the answer has the two significant figures and the same number of the figures as the least accurate known quantity be multiplied. There are two useful rules of the thumb for determining the number of significant figures. In first, considering multiplication and division, it is followed. So in multiplying or dividing two quantities, the number of significant figures in the product or the quotient is the same as the number of significant figures in the least accurate of the factors being combined, or rather less accurate means having the lowest number of significant figures. So if you multiply or divide less sig figure. To get the final number of significant figure, it is usually necessary to do some rounding. If the last digit drop is less than 5, simply drop the last digit. If the last drop is greater than equal 5, raise it by 1. So apply the multiplication rule for significant figure. So a carpet is to be installed in a room. The length is 12.71, right? And the width is 3.46. Right, find the area. So we have to multiply the length by width. And how many significant figure we have? We have a 3, so it's gonna be 43. So it's gonna be 44.0, right? So because the answer is 43.9. So the count is significant figure in a number. So first, the carpet is okay. So the strategy is count the significant figures in each number. The smallest result is the number of significant figures in the answer. So 12.71 has 4, 3.46 it has 3. So we multiply, it's gonna be 44 because it should be only 3 significant figures. So reducing 43.976 to 3 significant figure, use the rounding rule. So adding 1 to 9, which makes it 10, and resulting we carry the 1 units to the units place. So what would the answer have been if the width was the 3.460? So 1, 2, 3, 4, 5 is going to be the 3.460 times 12.71. The answer is going to be 43.97, right, or 98. Alright, so I'll repeat the problem, but with the different width, or like the 9.72, the 9.72 times 5.3. So the two significant figures is gonna be 5.2, right? Okay. Right. So zeros may or not be significant figures. And I believe this is an important fact for you to know it. Zeros used to position of the decimal points in such numbers. Like, for example, we have a 0.03 and we have 0.0075. Are not significant, but are useful in avoiding errors. Hence, 0.03 has 1 significant figure and 0.005 has 2. When zeros are placed after other digits in a whole number, there is a possibility of misinterpretation. For example, suppose that mass of the object is given as 50 grams. So this value is ambiguous because we do not know whether the last two zeros are being used to locate decimal point or whether they represent significant figures in measurement. Using significant notation to indicate the number of significant figures removes this ambiguity. In this case, we express the mass as 1.5 times 10 to the 3 gram. If there are two significant figures in the measured value, 1.50 times 10 to the 3. If there are three significant figures, so 1.500 times 10 to the 3, right? So if there are 4. Likewise, so 0.001, how it goes 1.5 times 1, 2, 3, -4, right? So it has the 3 significant figures. 3 zeros between the decimal point and the digit 1 in the number are not counted as significant figures because they only locate the decimal points. In this book, most of the numerical example and end of chapter problems will yield answers having 2 or more significant figures. So that's also important. Calculators were designed by engineers to yield as many digits as the memory of the calculator chip permitted. So be sure to write the answer down, okay? Now, for addition and subtraction, it's best to focus on the number of the decimal place and the quantities involved rather than the one number of the significant figures. When numbers are added or subtracted, the number of decimal place in the result should equal the smallest number of the decimal place of any term in the small difference, right? For example, if we wish to compute 123 zero decimal place or 5.35, the answer is 128. And not 128.35. If we compute the sum 1001 for decimal place, right? So the result has the correct number of decimal place, namely 4. Observe that the rules for multiplying these significant figures do not work here because the answer has 5 significant figures, even though one of the terms in the sum pointer has only 1 significant figure. Likewise, if you perform subtraction, so here is 1, 2, 3, 4, 1, 2, 3, okay? So we put 3 decimal places because each term subtraction. So for decimal place for subtraction or addition, you count after 0, right?